because I forgot to press record last time. This will definitely be posted on YouTube. I will post it probably tonight, and then if you guys want to check it out, you guys can. But yeah, so last session we went over modules 1 to 3. I kind of like said that a lot of the stuff like in modules like 1 and like 2 is things that you might not like see that much on the exam, and that's kind of true. Like you might see something like density for sure. That's definitely something you might see. But yeah, like really the bulk of like modules 1 to 3 would be like two with like electrons and all that, and then three with periodic table. Is three electrons as well? I guess three is electrons, yeah. Two is like the experiments, and then three is like the actual electrons. But yeah, like really want to spend a lot of time on like module 3 because there's a lot of stuff there like with quantum numbers and periodic table trends and stuff. So just keep that in mind. And yeah, for last session, honestly, like what we did is it wasn't that great. We were like I was kind of yapping a lot. This time I hope to, I guess, like engage you guys a bit more by adding some questions. I took some questions from my practice exams, and some of Professor Yusuf's exams. I took some questions there and I picked them out. And so like I'll like yap a little bit about whatever stuff, and then we'll do those questions and we can try to answer them together. But yeah, with that, I will start screen sharing and let you guys just I'm gonna get started. Do you guys have any questions or anything? Like initial questions, studying. Okay. I hope you guys are doing good. I know that you guys all have calc, bio is Thursday, and then your data and writing class. I don't know. Every teacher is different with that. But yeah, I'm gonna start screen sharing. I'm not good at small talk. Okay. Alrighty. Where is it? Okay, let's go over here. All right. All right. So this is module 6. So we're gonna go over modules um 4, 5, and 6. So 4 and 5 kind of go hand in hand, and then 6 is like some math. Like 6, module 6 and module 7 go hand in hand together. But we're just gonna go over the first part of module 6 because module 6 is, like it deals with math, right? And module 7 really goes into the stoichiometry, which we'll deal with next time. But before we do that, so I'm gonna just scroll all the way up. We're gonna talk about Lewis dot diagrams. Did everyone? I hope everyone can hear me. I can't really see the chat, by the way. If you guys send me messages through the chat, I won't be able to see it because I'm on my iPad. So if you guys have a question, like don't be afraid and like unmute and let me know because I will slow down or whatever you need me to do. But yeah, anyways, so we're gonna get started. We got bonding, right? Lewis dot diagrams. This is all like basically how do compounds and molecules like actually form itself. And they take these electrons and they share these electrons in some way. So we have ionic bonds, which is a direct transfer of electrons, meaning that you got sodium, right? And you got chlorine. What happens is one electron from sodium goes directly to chlorine. And that's because it fulfills its octet, right? You guys remember what octet is? It's just basically the rule that um, a like an atom wants to be isoelectronic, right? Or it wants to have 8 electrons. And the reason being is if we do I have a periodic table here? Where's my periodic table? Is my periodic table here? Yeah, right there. It wants to be isoelectronic. And the reason being is when you lose electrons or gain electrons, right? It can be isoelectronic with its noble gas. So for instance, with sodium, right, it's going to lose an electron to become isoelectronic with neon, right? And then likewise, chlorine is going to gain an electron to become isoelectron with argon. So that's kind of why that octet rule is there, but just make sure you understand what the octet rule is, which is right over here, right? So noble gas configuration, okay? And so here's like a pretty good frame of reference. On the periodic table, I believe if I have it here, you guys have this chart with all the electronegativity tables. So even if you make an assumption, right, like you can obviously assume like a metal with a non-metal will be ionic for sure. But like don't always assume. Like sometimes I remember I had a question once where it talked about what is the bond between carbon and bromine, right? And if you look, carbon is 2.5 and bromine's 2.8, right? And I thought, without looking at it, that it would be polar covalence, right? But if you look over here, it isn't. It is non-polar because it's a zero point 0.3 difference, right? If I pull this over here, I'm kind of going a little fast here. Carbon has a 2.5 difference, right? And then bromine has a 2.8 difference. And they were asking in the question, CBr4, like what kind of bonds does CBr4 have? And it's supposed to be non-polar covalent. So always like if you don't really know, if you're not sure, make sure you just check out the electronegativity table on the reference table. But anyways, so we got like electron configuration. We talked about this last time. And it's just important because then, yeah, it goes into predicting ionic compounds, which is really important. Um, because, yeah, like there's some questions for sure that will be asking you to do that. And yeah, let's try to do these couple of questions. Yeah, I'll give you guys some time to do it. I'll give you guys like a minute to do it. All right. So, yeah, let's try to do this. Oops, sorry. Ah, wait, wait. Yikes. Okay, I'm just gonna leave it. Yeah, take some time, try it out. Not bad. Alrighty. Would anybody like to volunteer to answer the first question? What would the chemical formula for silicon nitride be? Okay. I'll guess I will do it. So silicon, right? First off, we should look at our periodic table. And remember what we said. I don't know if we said this last time, but basically, elements within the same row have the same electron configuration specifically, right? So we know that carbon has like a +4 -4 sort of charge sometimes, right? It can bond with four different, like it can bond four times, right? Um, that's why you have something like CH4, right? Um, and then yeah, so it's likewise silicon's right under it. So and we also know that nitrogen would have a -3 charge typically, right? So because of that, you got C4 and then N, or sorry, Si4 and then N-3, right? So this would probably be +4. And then you crisscross applesauce and you get E. Oh, all right. Does that make sense, everybody? A key. Yeah. All right. Thank you for that verbal response. All right. Number 7. So barium sulfite, right? Uh, I just said the answer. Oh, so the whole takeaway here is you want to make sure you know the polyatomics, right? Sulfate, right, is an extra oxygen. Anytime you see like eight and ite is always one less oxygen. So like chlorite, right? Chlorite versus chlorate. The difference between those two is one oxygen. So this is chlorate, and then this over here is chlorite. So just a little bit of naming convention here. So this would be barium sulfite. And remember, you don't use the um, Roman numerals because the Roman numerals are only given for transition metals. Does anybody remember what the exceptions for the transition metals are in terms of Roman numerals? Like which metals do we not use for Roman numerals that are in the transition metals? Do you guys know off the top of your heads?
Is it like zinc, silver, and like something else like CD?
Yeah, you're right. Exactly. So zinc, right, always has a +2 charge. You don't, it doesn't vary. Silver always has a +1. You guys are very familiar with that. And it's actually cadmium, and cadmium has a +2 charge, but that one's not as used that one's not used as much. So good, good for remembering that. But anyways, let's keep going. So this is like the properties of ionic compounds. Make sure you guys have a good idea of this because there definitely could be a question like regarding this because it's a good question even for the MCAT as well. So let's try to answer this question. All right, I'll give you guys 30 seconds to do this. All righty. So just like I added this question because I feel like a lot of you guys might get tripped up on like the wording and you guys might be a little confused about like how to really like go about these questions. So with this kind of question, what tend to do is I kind of cut out all the fluff. There's a lot of words here, but I basically want to get the main idea out of each answer choice and the question as a whole. So this question's asking about something with ionic compounds. And like, I guess they're probably going to talk about ionic compounds in the answer choice, right? So that's all I need to think about. And we need to figure out which thing is not right. Yikes. So which one's not right? So on my answer, like if I'm doing this on the exam, I would underline something like I'd underline ionic compound, bonding, and then also incorrect because that's what we need to figure out. So we see here in ionic compounds, oppositely charged ions are held together by electrostatic attractions. That sounds correct, right? We think about like NaCl, right? They are oppositely charged and they're held together by those kind of attractions. So that's correct. So yeah. All right, let's continue. B, ionic compounds commonly form when atoms of two nonmetals react. That seems like it's very incorrect. So I'm just gonna already circle that. I don't even need to check of other things because that is definitely incorrect. But yeah, like even if you didn't know, you can still like look through this. Okay, when ionic compounds form, electrons are transferred. All right, we went over that definition. That's correct. And then ionic compounds tend to have a higher relatively melting points. I know this as a fact, and this is because my high school chemistry teacher used to tell me that NaCl has a melting point of like 800 degrees Celsius. That's just something I always know. You can try to think about it. If not, yeah, I'm telling you guys that NaCl has a melting point around 800 degrees Celsius, which is crazy. So yeah, B would be the right answer. Any questions about this? Okie dokie. All right. So yeah, covalent bonding is sharing. So instead of it being a direct transfer of electrons, this time you're sharing this. And this happens typically with nonmetals. Um, and so yeah, we first have nonpolar covalent. This is when the electron negativity difference is essentially zero or less than zero point 0.4 in this case. So technically CBr4 would be a nonpolar it would contain nonpolar covalent bonds. And then likewise, polar covalent, right? It has an unequal sharing of electrons, right? So something like HF, F is super electronegative. We talked about this in module 3. And so because of that, it's pulling more electrons. And so another way to think about this is that this has a fluorine has a dipole of it's partially negative. That's what it essentially means. This is a partial negative charge, and hydrogen has a partial positive charge. I'm only putting this here just because on the practice final, there is a question that is on there that you might get a little tripped up with. But this is kind of the symbol for partial charge. He doesn't really put that on the slides, which kind of is annoying, but it kind of makes sense intuitively. Like fluorine has electron has an attraction for electrons, and so it's going to have a more negative charge, whereas hydrogen with a smaller attraction for electrons will have a more positive charge. But anyways, let's try to answer this question. I'll give you guys 30 seconds or I'll give you guys a minute to do this because reading. But yeah. Alrighty. What is the answer to this question? It'd be E. All right. We just went over it. So when you do these kind of questions again, right? There's a lot of words here, but you really just want to cut out the fluff and really get the main idea of each thing, right? So polar covalent, okay, unequal sharing of electrons. Just it's like a definite, it's like vocabulary at that point, right? And so you pick the one that says unequal sharing, right? And you it's obviously electrons, not protons. So that's kind of like the whole idea with that. Okay. And then, yeah, you want to make sure you have in mind what properties of molecular compounds are. I tend to think about um, like sugar, right? Like sugar water or like chocolate milk, right? They're not, it's not conductive. It is soluble in water for some, for the most part. I mean, some molecular compounds are soluble in water. They have low melting and boiling points. The bond strength in comparison to ionic compounds is lower. Um, and yeah, non-metals react. Yeah, non-metals reacting with other non-metals. Yeah. So this is just like a summary of what we talked about. So let's try to do this question. Um, yeah, this involving oh, the electronegativity chart here. So I'm gonna just make this bigger, and then you guys can try it out for yourself. Oop, there you go. I'll give you guys a few minutes, I'd say, to do this question. Let me see if I can join on my phone. Might not be the smartest decision. All right. If you guys have questions, you guys can text me in the chat as well because I just joined with my phone. I just moved it across the room so that it's not that loud. But when I'm quiet, I will look at the phone and you guys can answer questions or ask me questions. Yeah. But yeah. All right. I'm going to go over this because it's not that deep. Basically, all you have to do is find well, you might not know what dipole even means, but it kind of is annoying. I wish he went over that, but it basically just means which one's polar. Dipole means polar. You guys will learn about it more next semester. I don't know why he says this terminology without really explaining it, but I mean, you can kind of pick it apart when you're like doing questions like this, right? You always want to make sure you read these words and like really understand what they're saying. When you say something like pole, like you can think of like polar, right? It's kind of it's kind of sucky. But like yeah, most times like if you don't know how to do it, breaking up the word is really important. But anyways, yeah. So we just use the periodic table for this or the electronegativity thing. So this sulfur and carbon, right, would be 0, right? So that's not 1. E and Cl3, 2.1, and this has a point 9. So yes, that one definitely. Let's see. BeCl2. That one's good. Or is that I think that's ionic. BeCl2. Is that ionic? Forgot what it is. You got to make sure you have like the ranges in mind, I guess. So, oh, wait, 1.8. Okay, anything above 1.8. So I think that's actually in the range of polar covalent. So make sure you have that range in mind. But yes, that works for sure. Silicon bro or CF4, that's definitely polar. So yes. Um, Silicon bromide, SiBr, that is polar. H2C Se, H is 2.1, Se is 2.4, so not that one. And PF3, that one definitely. Anything bonded with fluorine um is definitely gonna be polar. So this answer would be E. All right. Any questions? All right. Moving on to yeah, here's some questions here about decreasing polarity, right? We basically did the same thing here, except instead of really showing decreasing polarity, we just identified which one's polar, which is basically the same sort of thing. And this is what I mean when it's like there's a lack of originality with some of these questions, because at some point you have done everything, you have to just kind of trust like that you have every tool that you can to like answer these questions. Like if there's a question that you might not know, like for example with this question, right, you already like if you were not given this, right, you'd have to think to yourself like, okay, like what do I have in my tool belt that can answer this question? And that's like the main idea I really want you guys to get into your brains, that like you guys have all the answers to everything. You just need to try to find it in your brain sometimes. And it can be hard, but that's why practicing like this is really good. But anyways, let me continue. So now we're talking about chemical nomenclature. This is not this is definitely gonna be like one or two questions maybe. I mean, this is like in every question basically. Like this idea of like, oh, like if I tell you silver nitrate, you have to know what that is basically. Um and so, yeah, we talked about this. These are the exceptions to the naming stuff, right? When it comes to um, like any other transition metal, like copper, for example, or iron, right? You use the Roman numerals. Okay. And then likewise, polyatomics also are important, right? So you don't really change the name of the polyatomic, but you consider the metal ion or the non-metal, the metal ion or the non-metal anion when you do this. So like ammonium bromide, right? Bromide would be changed, right? Something like cesium cyanide, right? Cesium's not changed, cyanide not changed. So like just keep in mind the naming code conventions and whatnot. Hydrates, honestly. Oh, does someone have a question? Or anyone have a question? Okay. Yeah, hydrates, they're just dealing with water, right? I'd see like a good question for him to ask is like, what's the mass percent of water in this compound? Right? That's an easy question to ask because it tests molar mass and it also tests hydrate. And it tests like mass percent, right? So yeah, you want to just keep in mind how this thing works. It's just basically a compound that has water in it. And it's typically named using this like no name thing, right? It's the same thing as the covalent nomenclature stuff. But yeah, okay. And then yeah, binary covalent. This is with covalent stuff. It's the same thing with hydrates where you really name it. You don't name the first one if it's one, but then after that you name everything. So like for instance, what I mean by that is like this is nitrogen dioxide, and then over here this is dinitrogen monoxide. Sorry for my terrible handwriting. Oh my gosh. Oh my gosh, I'm gonna be a doctor. Oof. Okay, anyways. Yeah, so you want to make sure you just have a good idea of like how to name these sorts of things. And I think the prefixes are pretty self-explanatory. I think like when I see hex, I think six because of the X. Um, Hept, the T, looks like a seven. Something I don't know. I'm just trying to make you guys remember it somehow. Nana nine, Deca, yeah, uh, Diaz. Yeah. Okay. Anyways, just try to make sure you know the prefixes because it'll be important. And then naming acids, he's not really the type to like ask a question about like, like what's the name of this acid. He would do something more of like, giving you guys a neutralization question and asking you guys to solve for it, right? But just yeah, keep this in mind. This is more important for next semester as well. Um, yeah, like if he could say something like sulfurous acid, um, I did not spell that right. Sulfurous acid, like reacting with NaOH, right? And you have to know what sulfurous means, right? So we know sulfuric is H2SO4. So sulfurous has to be H2SO3, right? So you want to just keep in mind these naming conventions and whatnot. Again, right? Is like weaker than ick, right? It just makes sense, right? Sulfuric is like, like I think of like a German scientist, like sulfuric, right? Sorry. Anyways, and then sulfurous, it's like sulfurous, like I don't know. Okay, anyways, I'm gonna stop making a fool of myself. Let's get to the question. Let's try this question out. All right. So try to answer this question. Give you guys like 30 seconds to do these. Alrighty. What is the answer? The answer here would be C. We can tell this because manganese is a metal and this is a non-metal. So this would definitely be something that's ionic. And so something with tetra, right, is automatically a giveaway that that would be like this is the incorrect one because tetra, any prefix one would be either in a hydrate, which is always after like a water, like hydrate, like hexahydrate, or the prefix will be covalent, right? And so this does not fit those criteria. So that's why C is the right answer or the incorrect right answer, if that makes sense. Okay. All right. I'm gonna move on. So now we're getting into the Lewis symbols and structures and all that. So yap, yap, yap. All this is yap. Lewis structures, right? We talked about electron configuration. This also applies to the Lewis structure, right? So something like fluor or something like sodium ion would be something 1s2, 2s2, 2p6, and 3s1, right? And that one refers to that valence electron. So Lewis dot diagrams always show the valence electrons. So that's just the big idea. All right. So on the reference table, you have all of the valence electrons here. What do I mean? Let me go back. So I talked about this last time, but basically, if we, I'm gonna expand on it, right? We know that like each number or each row represents a principal energy level. So if we look here, right, let's see three, and we want to know how many valence electrons does sodium have? boom, it has one valence electron right there. If we want to know how many valence electrons chlorine has, we count from left to right. So chlorine has one, two, three, four, five, six, seven. All right. So you can count the valence electrons by using the periodic table. So like something like carbon. Carbon has four valence electrons, right? If you go from left to right. The only thing is when you get up to like this area over here, it might get a little confusing because you have this 3D orbital. But again, right, this is all these d orbitals are one less um like they're always one principal energy less than like the valence electron, right? So in this case, this would be 4s2, right? And then 4p6, right? 3d10 is still is an inner electron thing shell that's getting filled, right? So if I asked how many valence electrons does gallium have, Ga, you wouldn't say um one, two, you wouldn't say 13, right? You would say only three, right? And so this is again another like connection where we're seeing how um yeah, like the you can obviously like answer it by looking left to right, or if you just know the valence electrons in the row, like they all are going to have similar reactivity, right? So boron has three electrons, aluminum has to have three electrons, and then gallium would also have three electrons, and then everything else theoretically would also have three valence electrons. And then likewise, like carbon, silicon, germanium, right? Those will all have around four valence electrons. And then likewise, nitrogen, five valence electrons, all right? So just keeping this in mind is really good and it will help you out a lot with the list structures. But anyways, so yeah, and you always want to make sure you know the octet rule and duet rule. I'm gonna explain how to like write this out, right? This is a basic one. So we know water is H2O. If we want to write out this valence electron, first things or the loose dot diagram, first things first is you want to add up all the valence electrons, right? So we have two plus so we every hydrogen atom has one valence electron, and then every oxygen atom, if we look at the periodic table, and also like you can memorize it as well. One, two, three, four, five, six, right? Oxygen has six valence electrons. So there's two plus six, right? Which means there's eight electrons in total. So that means that in the in the Lewis dot diagram, there needs to be eight electrons shown. And so if we see here, right, if I draw out this water molecule in this way, right, there's at least one bond, right? One bond, right? And then we put two electrons here, we see that we're able to represent all the electrons using these things, right? So with hydrogen, you're going to follow this duet rule, which means hydrogen's going to have two valence electrons, like it wants to have two electrons. And that's because in the first principal energy level, there's only two valence electrons or there's only two electrons in the first principal energy level. The oxygen, right, sharing these electrons will actually have eight electrons. And this is why these compounds form. So this is like a very easy, like covalent structure to draw. There's going to be harder ones for sure. Um, yeah, so we talked all about this in class. And then here's some exceptions, right? You don't really see this as often, but something like nitrogen monoxide, right? Those have 11 valence electrons if you count them up in total. So you don't really see this as often. Second one is like electron deficient. This one you might be seeing, right? We saw it on one of the questions before, but something like beryllium dichloride, right? That's something that will have less electrons. So specifically, it's beryllium or boron. Those two atoms are sufficient, like they'll suffice if they don't have a full octet. And that's just something to keep in mind. And likewise, anything that has access to anything that has access to the third principal energy level can have more than four bonds, or can have and can surpass the octet rule, right? So like as we see, right, phosphorus is in the third principal energy level. We see that phosphorus can bond with more than like four things, right? We see that it can bond with PCl5. Even though it doesn't follow its octet, because it has access to that 3D orbital, that's why it can do that. So that's just some things to keep in mind. Here's like some practice. I submitted, this is all the SI slide. So if you want to do that, you can. And then now we're talking about formal charges. All right. Does anyone have any questions about Lewis dot diagrams or anything like that? Okay. So we're going to get into some formal charges. So formal charges, this is the formula for this. And what it represents is it represents the valence electrons minus non-bonding electrons, or I'd say just like single electrons, and then minus bonds, right? So what do I mean by that? So if we're looking at something like sulfate, right? If we look here, it has a sulfate has a -2 charge. And if we actually count up the valence electrons, so oxygen, right, we said has 6 valence electrons. If we count up the single ones, right, that'll have 6, right? There's 6 single ones, and then there's one bond, right? So that's gonna have a -1. So this oxygen's gonna have a -1. This one's identical to this one, so this one will also have a -1. Here, this one is going to be 6 minus 4 minus 2, right? So that's 0. And then that's also 0 because it's identical. And then sulfur has 6 valence electrons. It's right under oxygen. So that will be 6 minus 6. And there's no single electron. So that will also equal 0. So this is 0. And as you can see, the thing I want to point out is that the charge of the formal charges equals the overall charge of the molecule. And that's typically what happens. So this is a good way to check your work as well. Um, yeah, so here's like you can practice this if you want. Resonance is really important. So resonance structures are basically like different Lewis dot diagrams that you can draw that um, should, in theory, have the same amount of electrons. And yeah, they should be, yeah, it's basically, yeah, structures that have different like sharings of electrons, but ultimately like are part of like the overall compound theoretically. So like technically, right? Like what Professor Yusa said is like you're not gonna actually have one double bond there, one double bond there, and one double bond there all the time. Like, or you're not gonna have it like 33% of the time, because this is what this picture implies, right? You're gonna have a superposition of all these three compounds all at once, right? So instead of it being a double bond here, a double bond here, and a double bond here, it's gonna have to be like a partial double bond in all three of these oxygens. That's just an idea to keep in mind. So it's like he called it a superposition at one point, but yeah, it just is whatever, right? You guys can practice writing these structures out if you would like. Let's try to do this question. I noticed that I made an error. This is supposed to be iodite, and then this is also iodite. Okay, so try this question out. I know you guys might have done it before, but let me know if you guys have any questions about it. All right. I'll give you guys like I should give you guys like 5 minutes to do this. So I'll give you guys some time to do it. Ooh. Alrighty. Oh, DBA. I don't know. Okay. Um, hey guys, sorry, some technical difficulties. Um, sorry. Let me see. Did the recording stop? Oh no. Oh no, the recording's still going. Okay, good. All right, I'm gonna screen share quickly. Sorry about that. Okay, gotta keep going. Gotta keep going. Okay, so we got this question here, right? We got iO2 minus, right? So first question's asking about non-bonding electrons. Second question's asking about resonance structures can be drawn with this ion. And then third is asking about a true false question about the ion. Oh wait, this is the yeah, the iodite ion. Yeah, this is yeah, iodite. Okay. But yeah. So the first thing we want to do is we want to draw out the Lewis structure because that's what's asking here. So we see here that I is going to be 7 valence electrons. We can see that using the periodic table. Okay, right here, periodic table, 7 valence electrons. Just make it larger. Um, then oxygen is going to have 6 valence electrons, right? And there's 2 of them. And then we're going to add +1 electron because it's negatively charged. Okay, that's the first step. This is like the most important step. So we see here that's 12 and then 20 total electrons. All right. Does that make sense? Okay. So now what we're going to do is we're going to, you know, bond them accordingly, right? Um, and what we'll see here is that, like, if we just do it like this, like if it's just bound with single electrons, that wouldn't work out. Just because it would look like it's bent, but it doesn't minimize formal charge. So that's not the right structure, right? What would be more practical is for there to be a lone pair like that, like this. Sorry, not a lone pair, a double bond. So you see here, it's like boom, boom, right? Like that. Okay. And so when we see it like this, right, we see that this has a zero charge, this would have a zero charge, and this would have a -1 charge. This makes sense. Okay. So that's the kind of way I would go about writing these structures. Like I just like write out the total electrons and then write out like a structure I think would work. And then if it doesn't work out, then like, yeah, can I minimize formal charges? That's like the guide of like trying to do this. So now looking at this, we see that this is one lone pair, this is second lone pair, third lone pair, fourth lone pair, um, fifth lone pair, sixth lone pair, seventh lone pair, right? So this answer choice will be choice D, 14 lone pairs. All right. So that's, or sorry, 14 non-bonding electrons, right? Or 7 lone pairs. Okay. When I say lone pair, it just means that there's a pair, right? So 7 times 2 is 14. All right. So how many resonance structures can be drawn with the iodide ion when minimized formal charging? When minimizing formal charge on ions, right? So we know there needs to be a -1 charge. And so we could do something like, um, yeah, we could do something where it is I, O, and then O, like this, right? That's something that minimizes formal charge. Okay. Typically, you wouldn't do like something like this where you put a double bond on both of these and then um yeah, you wouldn't do something like that. And the only reason why is just because yeah, you wouldn't want a -1 charge on the iodine in this case. Oxygen would be a lot better to have that -1 charge. So like minimizing formal charges also means that you yeah, like you want the negative charge on the ion or the atom that you really want it on. So yeah, the answer choice for this question would be choice B. All right. So it's equivalent resonance structures, right? So there's this one and then this one, right? So this is the two structures. Okay. And then likewise, the iodide ion, right, contains an atom that exhibits the exception to the octet rule. Iodine can do that. So that's why that is true. Okay. Sounds good, everybody? Any questions? Okie dokie. I'm gonna move on. So yeah, now we're talking about molecular blah, 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 structure and polarity, right? So we're gonna talk about this Vesper theory, okay? Whew, all right. Before we you know, yeah, so obviously you want to make sure you memorize all of these, right? Make sure you know the electron arrangement. I'm not going to spend so much time on it, but just keep in mind a couple of things. I'm going to point them out as we go along, right? So this is like some notation. This is how he likes to explain it. Um, yeah. So you see all of these molecules, right? Yeah, like make sure you know electron arrangement and the difference between the two. Electron arrangement refers to how many electron domains are there. Molecular structure refers to the name. And then, yeah, I'm gonna move along because I'm kind of not doing good on time. But yeah, one thing to keep in mind, right, is these structures, like these electron arrangement structures, anything that is planar, so like what's it called? Square planar, right? Um, and that's pretty much it. All of these like electron arrangement structures are technically non-polar, right? So their arrangement, right? Even if you have polar bonds, it would be a non-polar molecule, if that makes sense. I'm just saying this because I don't really know if he really explains this well because I feel like he asks kind of questions about this, but like these arrangements like imply non-polarness, right? So something like CH4, right? CH4 has non-polar has polar bonds. C and H are polar. Or actually, no, CH I think is a non-polar bond. Something like something like CF4, right? Has polar bonds, but then because of its electron arrangement, it has a symmetric distribution of electrons. Um, yeah, so I think there's like a polar, asymmetric, non-polar, symmetric. Snap, yeah, snap. That's like the way to think about it. So symmetric is non-polar, and then pole asymmetric is polar. I don't think he's gonna ask a lot of questions on this because it's more for the next semester, but you never know. And then anything that's bent, trigonal planar, seesaw, square pyramidal, all of these, except linear. Linear is actually non-polar, but all of these other structures are polar. So linear is the only one that's not polar. I already sent like a summary sheet of it, everything like in a previous email. So if you guys want a more detailed review sheet of this, like let me know or go through the emails and figure like find it or ask me whatever works. Sorry. Okay, anyways, I'm moving on. So we got to keep going because there's a lot to this. Yeah, so molecular polarity, that's what I'm trying to talk about here, right? So as we know, like something like CH3Cl, right? Um, if we draw out the structure, it's gonna be something like this with Cl, right? Because there's a Cl here, it's gonna be polar, right? So that's why this molecule is polar. But then something like O double bond to O would be non-polar molecule. So again, you just want to keep in mind this like polarity stuff, and if anything, memorize it. But yeah, so here's some questions. Yep, 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 yep. I'm gonna skip this. This is one of the questions on module on like the second practice exam I gave you guys. So I'm gonna skip this just because for the sake of time, I'm gonna try to go over module 5 and 6 because I think 6 is more important. But yeah. All right. I'm gonna move on. So any questions about that or anything like that? Okay. So I didn't realize how much time was being spent. But anyways, so this chapter, modules 5, is not that significant, honestly. Like we got sigma bonds, pi bonds. That's pretty much most of this chapter, and then hybridization. So like something like this, when you count sigma bonds are the single bonds, right? So the first bond in between a atom. So like all of the things I'm circling like count as one single bond, right? A pi bond would be anything beyond a single bond. So like there's one pi bond in this double bond. A double bond consists of a sigma bond and a pi bond. A triple bond consists of a sigma bond and then two pi bonds. I am not writing this out well, but yeah, that's like the whole idea. That's pretty much most of this chapter, honestly. And then hybridization. You do not need to know most of this stuff. I don't think he's going to really ask a lot about this stuff. But yeah, the TLDR is hybrid orbitals are is what the name suggests, right? It has a hybrid orbital. So instead of it being S and P, it's SP, right? So like that's the whole idea. And the way you do that is you just look at the electron density, right? So if we look, I'm sure there's an example of this, right? Like this is a question you definitely could ask, right? Because it's an easy question to answer, and like it's not that bad. So like something like this carbon would be sp2, right? Because it has one, two, three, right? sp2, right? There's the exponents add up to three, right? In this case. So that's like the whole idea. Um, yeah. And then here's like double bond, triple bonds. They're not that important. Um, and then yeah. We could spend like 3 minutes on this question. I think you guys can do this pretty well. So let's try to spend some time doing this. But yeah, okay. So it's 6:33. I will get you guys back.
I can't.
This is recorded, everybody. So if you do something very embarrassing, um, there will be record of it. And also, whoever joins their NYT email is logged because that's how it works. Yeah, don't be stupid. All right, I'm gonna get started. So basically, for this question, all you have to do is count the sigma bonds, right? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then 16. So that's why D is the right answer. How many, so you want to make sure you just know the symbol between sigma and pi, right? Everyone knows pi. Sigma is this bond, the symbol. How many sp3 carbons are there? We see that there's 1, there is 2, and I think that's it. Yeah, there's only 2 sp carbons. All right. So where is it? That is right there, B. Okay. Oxygen's connected to the carbon here. This is not a bond. I should have erased that. That's my bad. But if you see, this is the oxygen, and then this is the oxygen. And so this oxygen here is 0, and this one's also 0, because if you do 6 minus 4 minus 2, that's the same thing for both of these, right? That would work out for both of them. So that's why it's C. And then the molecular geometry around carbon A, right? We see that it has a 1, 2, 3. So it would be probably trigonal planar. All right. So that's because it has 3 electron densities and it has no lone pairs attached to it. Okay. Does everyone get that? All right. Now we're getting into module 6. I don't mind going a little bit over time if you guys are okay with that. I feel a little bad that I spent so much time on module 4, but we will see how this goes because there's a lot of questions here, I'm sure. But anyways, let me go all the way up. So module 6 consists of all the fundamental like calculations that we need to know for module 7, essentially. So all the stuff for like molar mass, um, mass percent yield maybe, molarity, and then the additional like empirical questions that we always are annoyed with, I'm sure. But yeah, so we need to know diatomics at this point. That's just something you should have committed to memory. And then likewise, what's it called? Yeah, formula. Yeah, you should just know these formulas. I mean, these vocabulary words are just things you should know. Empirical formula, you definitely should know. There's definitely gonna be some kind of question about this. Yeah, and then isomers, right? Those are just chemical formulas that have the same. Sorry, they're the same chemical formula but different structure. So if you see here, this doesn't really mean much to you right now, but represent carbons, the angles here or the corners. And so this molecule has carbons, right? And then, yeah, like if you think about it, I'm not gonna explain it just because, yeah, this is an organic chemistry concept, but basically it's the same chemical formula, but different structure. That's the whole idea. Okay. And so then we move on to moles and mass and everything, right? And we talk about how we can use the molar mass to convert from grams to moles. And then from moles, you can go to a bunch of things, right? So like this is the whole idea, right? You can go from grams to moles, and then moles, you can go to particles with Avogadro's number. And then we also learned in the gas law constant that you can, if everything's at SCP, you could use 22.4 liters per mole to convert to volume. So that's why this like mole is really significant. But yeah, let's try to do this question. Give you guys like 3 minutes to try to do this. I'm giving you guys like less time to do it so you guys could try to do it fast. I like we talked about how to do these kind of questions before, so and you guys have done these kind of questions before, so try to do it faster than you typically would do it. But yeah. Alrighty. So this question here, what it's saying, it looks more complicated because he added a bunch of yap. Um, but basically, the whole idea with this is that they give you the mass percent of water, right? So it's kind of like a hydrate question, and then they give you the mass of the total Earth, and they're asking you to find the molecules. So I always like to use dimensional analysis to solve for this, right? So we know that if we multiply this number, 5.97 times 10 to the 24, and we multiply this by the decimal value of this percentage, so that would actually be 0.00023, right? That will equal the mass of water, right? So here's mass. This equals the mass of water. So let's do that. 5.97 times 10 to the 24, 0.0023. I honestly like taking, I'm gonna just write out everything in this math and then I'll put it into my calculator. That's kind of how I do it. So because we get the mass of the water, now we have to find the molar mass, right? To convert from mass to moles, right? So 1 mole over 18.016 grams of water, right? This is something I memorized. 18.1. If you use the periodic table, you can solve it yourself if you feel inclined to do so. Find the molar mass. And then after that, you multiply this for every 1 mole of that atom or molecule or compound. So H2O, there's 6.023 times 10 to the 23rd molecules. Okay. So that's kind of how I would do it. And then I would plug everything I did in the calculator. I use parentheses um, and close parentheses to make the fractions. And then when I use scientific notation stuff, I also put that in parentheses just so that everything is all good in the hood. So that's kind of how I do it. And your final answer should be choice. Did I put this in right?
You put grams. Isn't it supposed to be in kilograms to begin?
Ooh, good catch. Good catch. Wow, that is great. So again, so that's great. So that is amazing. Okay. So that means that for every 1 kg, there's 1,000 grams. Thank you for letting me know. See, I make mistakes just as much as you guys do. Um, no one's perfect. Okay. So with this in mind, let me add that. So it's just times by 1,000. So we're gonna get or 1 kg is one. I put 24, 5.97, 6.023 times 10 to the negative times 10 to the 20. Is it 23rd or 22nd? It's 23rd, right? Avogadro's number? Am I tripping? I don't know. Am I tripping? I am. Where's Avogadro's number? Avogadro's number. Is Avogadro's number here? Do we have to memorize it? I thought
I
it would
think
be
you
on
have to
the.
memorize it.
You have to memorize it? Oh my. Did I put it in right? 6.0263 times 10. Yeah, I put it in right. It's like slightly off. I don't know why it's off. Let me retry it. One moment. 5.97 times 10 to the 24 grams every 1,000 things, and then times 0.0023 times 1 over 18.016. 6.023 times 10 to the 23rd power. I'm getting something that's interesting. That's interesting.
Wait, would you have to multiply by 0.023% since it's saying that that is 5.97 times 10 to the 24th kilograms?
I believe, um, wait, can you repeat that quickly?
Because it's saying that 0.023% of Earth's total mass is comprised of water. and it's already telling you that that percentage is 5.97 times 10 to the 24th kilograms. So you don't have to find the percent, you don't have to find how much water is in grams because they already give it to you in kilograms.
Oh, so you're saying that this is the mass of the water? I'm pretty sure though, if I'm
Luke,
pretty sure, yeah.
I did the question. I got D. Um,
Do
I
you,
think you just like for what I did was I multiplied the 5.97 times 10 to the 24 by 0.023 first, and then I kind of plugged it in. I don't know if that changed anything.
did you use 0.023 or 0.00023?
The way that you wrote it.
Oh, so maybe I did some, I don't even, wait, so what did you change? Did you change anything from what I
I
wrote
didn't
here?
change anything. Maybe you're like not putting it in correctly.
Yeah, that's probably what I'm doing. But yeah, with this kind of question, they're saying that the mass of the Earth is the kilograms. Like, I know that the wording is like a little bit tough, but that's why you gotta make sure you really read it carefully. But man, why am I getting this wrong? Hmm, I don't know what I'm putting in wrong. Uh, 1 mole over this 0.00. Oh, I see what I put in wrong. Okay, I put in the 0.0023. I didn't put this in right. Okay, but yeah, the answer would be D. All right. But yeah, again, that this is the kind of question where you really got to read what you're seeing here. Um, it says, yeah, of Earth's total mass. So it didn't tell you, like, it told you the percentage of it, and then they tell you the mass of the Earth. It's really annoying because, yeah, like, it's not really clear, but that's why you got to really take into consideration that. But thank you for both both of you guys' input because I make mistakes, so it's good to hear about it. But anyways, so empirical and molecular formulas, right? This is where we talk about mass percent, which is what we just talked about, kind of. We talked about that with the water and the earth, but instead, let's say I'm talking about Cl, Cu, Cl2. If I want to find the mass percent of chlorine, right, I'll take the mass of the element in the compound um, divided by the total mass. So this is essentially just fractions and percentages. Like if you really want to boil it down, that's all it is. It's just fractions. Part over whole times 100. Um, I don't really know how many questions there would be asked about percent composition. There might be something where it's more, it might be something more like this kind of question that we just went over, where you're testing multiple things. But yeah, that's a good thing to go over, of course. And then we have empirical formula, which is really important. There's definitely going to be like one or two questions kind of on it, just talking about, um, yeah, like empirical formula using these percentages and converting them to masses, and then trying to find the empirical formula and then find the molar mass. Let's try to do this question regarding empirical formula and whatnot. So let's try to do this. I'll give you guys a few minutes to do this. And I should put up the thing here. Here you go. Alrighty, I'm gonna go over this quickly, right? So this is a classic empirical formula question where instead of like doing organic chemist, like an organic compound, we're gonna be doing 74. We're gonna be doing like an ionic compound, which is essentially the same thing. And so we see that zinc has a percent composition or percent by mass of 74%, which means oxygen has a 26%, right? So 74 and 26, right? So we're gonna assume like this is the amount of grams, right? And so first things first is we divide it by the mass. So this one would be 91.224. This is the molar mass of, or this is the atomic mass of zirconium. And then this one would be 15.99. This is oxygen, this is ZR, right? And so when we divide these out, we see that this would be 0.88, 811, right? Around there. This one would be 1.625, right? And so as you can see, next you divide by the lowest ratio, which would be something like this. And what you get here is you'll get a 1:2 ratio. So that means that the formula for this would be zinc or zirconium, oxygen with a subscript of 2. So now when we name this, right, we have to consider a couple things, right? This is a transition metal. We also know that oxygen always has like a -2 charge, right? So when you look at this, if oxygen has a -2 charge and there's not a -2 charge over here, what that must mean is that this has to have a +4 charge, zirconium. Why that is now we learned it in module 7 about the you know oxidation states, right? If this is -2, right, this has to be +4. That's one way to do it. So I'm gonna just stick with that way because that makes most sense. So the answer would be zirconium 4. There's no S. I don't know why there's an S in these. It's zirconium. Okay. And then over here, the type of bonding would obviously be ionic. All right. Any questions? Okie dokie. We'll do this question as well. Yeah, we'll spend like a minute, I guess, try to figure out if these are isomers or not. Alrighty. So for this, what I would do is just write out like how many carbons, hydrogens, and oxygens we see in each thing. So this one it would be HC3. There would be um 1, 2, 3, 4, 5, 6 hydrogens and 2 oxygens. Over here we have 3 carbons, right? We have 6 hydrogens, right? If we count them up, and we have 2 oxygens. And over here we have 3 carbons, 6 hydrogens, and then 2 oxygens, right? So the answer would be D. All right. Sounds good. We're moving on. Okay, so now we have molarity, right? This is just a nice little thing to kind of try to understand, right? The answer here, right, is yeah, 50 milliliters of propane is dissolved in 1 liter of hexane, right? So what is happening is hexane is the solvent and propane is the solute. And this is just basically, this is the most amount of this is the component the solute is the component that's dissolved, right, in the solvent and the medium that the solvent is in, right? So in this case, hexane is in the medium hexane is the medium and then propane is a solute, right? Okay. And so we got our classic dilution formula. And so here's a good question with dilution. I'll give you guys a few minutes to try to solve this out. Yeah, I'll give you guys a couple minutes to do this. You can use that dilution formula if that helps. Whatever works. Alrighty. I'm gonna go over this. So using C1V1 equals C2V2, we can solve accordingly, right? So we have 0.35 and we have x on one side, and then you have 5.9 times 10 to the negative 2 equals 4.8 liters, right? So we can solve for that. So what I'll do is I'll put 4.8 times 5.9 times 10 to the negative 2 and divide that by 0.35. And the answer I get is in liters. So I got around 809, 0.809 liters, right? And so it's in milliliters, so that would be choice E. All right. Okay, I'm gonna move on. So all of this stuff with mass percentage and volume percentage, I really don't see him asking questions about these kind of things. I'm going to be honest. So you don't really need to focus on it too much. I don't really think it's a significant part of this stuff, but I mean, just keep it in mind. I mean, mass percentage, it's all fractions at the end of the day, right? So volume percentage would be the volumes, like the percentage of volume, like the fraction of volume. The mass percent is the mass, um, fraction, right? These mixed units, mass volume percentage, I don't really see him asking these kind of questions as well. Again, it's still a fraction, grams over milliliters though. So like, and like five, like you let's say I dissolve 5 grams um of like NaCl in 100 milliliters of water. The mass percent or the mass volume percentage would be 5%. And that's because if I put 5 over 100 times 100, right, that'll equal 5%, right? So this is ml, this is grams. Okay. So that's kind of the formula with that, but you don't really need to know it. Over here, you don't really need to know it as well. Um, but again, like if you understand that the fraction aspect of it, will be able to understand it. But I don't really see him asking a question about these sort of things. I don't think he has in the past. In the practice exam I gave you guys, he didn't ask a question. I don't think he asked the question on my final. So I don't think he would ask these kind of questions, but in the chance he does, okay, just keep in mind what these things mean, right? You can memorize these formulas, of course, or you can understand it, right? Parts over a million equals mass of solute over mass of solution, if that makes sense. So parts per million, that's the way I think about it, right? Parts per million, so put a million under the parts, right? And likewise parts per billion. That's how this is the formula I memorize, but yeah. All right, so besides that, that's pretty much it that I had planned for today. Um, yeah, I'll stick around for like a few minutes if anybody has any questions. Hope you guys enjoyed this session and whatnot. I definitely enjoyed doing a lot of these questions. But if you guys have any questions, I'll stick around for like 5 or so minutes. I'm also gonna stop recording. So yeah, if not, have a good day, everybody.